Alright, excuse me, continuing with Lecture 6, the non-unit speed case of the Frenet Serret theory. For the non-unit speed case, we have to define the Frenet apparatus, meaning the tangent, normal, binormal, curvature, and torsion, in terms of what we've already defined for the arc length parameterization. So, consider a curve which, found my chopsticks. So consider a curve alpha, smooth, regular curve, nonlinear, in other words, acceleration is not zero, for which the arc length parameterization is denoted alpha bar. So this alpha bar, we've already defined tangent, normal, binormal, curvature, and torsion. So we can use our already defined unit speed quantities to define the non-unit speed quantities in the natural way. First of all, s is the arc length function, we're assuming. So alpha of t is alpha bar of s of t. That's the connection between the non-unit speed and the unit speed parameterizations of this curve. And then we define the tangent, normal, binormal, curvature, and torsion in the natural way. Oh no. Daniel's here. Daniel, I'm taping something right now, buddy. So, alright, so then if we differentiate alpha, so alpha prime of t, we have is d dt of alpha bar of s of t, like so, which is going to give us, Daniel, please stop that, d alpha bar dt of s of t times ds dt by the chain rule. Alright, but the derivative of alpha bar, remember, alpha bar prime is just equal to t bar in our current notation. So this is exactly t bar of s of t and times ds dt. Alright. So in other words, this gives us v times t of t, where v is the speed, it's ds dt, alright? It's the magnitude of alpha prime of t, actually. Alright. So there you go, that tells us the velocity is the speed times the unit tangent direction. In other words, velocity is speed times the direction of the tangent vector. That makes sense. Now, we can also do essentially the same calculation, for example, to calculate t prime. And by t prime I mean dt dt. Alright. So that is d dt of t bar of s of t. By chain rule, that is t bar dt evaluated at s of t times ds dt, which is the speed. So what that gives us is the speed times t bar prime evaluated at s of t. Okay, but we know the Frenet Serret equations give us that is exactly the curvature times the normal, right? And that would be evaluated at s of t. Okay, but in other words, we get v curvature bar of s of t times n bar of s of t by the Frenet Serret equation, first one. But this is precisely what we define to be kappa, and this is precisely what we define kappa of t, actually, right? And this is precisely n of t. And so what you see is the Frenet Serret equation for t is ever so slightly modified. It becomes the speed times kappa times n, right? That speed factor is new. Now, of course, this is consistent with our previous work because before v was 1. So likewise, we have the other two Frenet Serret equations just get multiplied by speed. So n prime is minus v kappa t plus v torsion binormal, and b prime is minus the torsion times n. Alright, and so there you go, those are the non-unit speed Frenet Serret equations. Now, I'm not sure, what is this, Dan? What am I looking at here? What is this? What am I looking at?
It's a Lego person.
A Lego person? That looks like a Lego robot. Is this some sort of Lego battle bot or something?
Yes.
Oh.
I'll show you what it can do.
Oh no, it lost its head! Ah! Okay, I'm going to go on. Alright, So in particular, you could you can see that the curvature and the torsion in the non-unit speed case are going to be a little bit differently defined. So let's see here how to go at this. I mean, for example, it turns out that the curvature is going to be equal to 1 over the speed times t prime dot n, where everything here is in terms of time, okay? And taking the dot product of the last one, the torsion, oh, I lost my speed factor, there's a v here. Torsion as a function of time is going to be minus 1 over v b prime dot n. Alright, so the definition of curvature and torsion acquires a speed dependence. Well, these aren't definitions, these are derived quantities in terms of a non-arc length parameterization for the curve. Of course, that is not unique. You can have many different, you can take the same curve and you can travel along at many different speeds, right? Okay, so moving along here, we should talk about acceleration just a bit, right? So I talked about speed, velocity already. So what about acceleration? Acceleration. So again, we just had that the velocity, alpha prime of t, was equal to v t. And then, so if I differentiate this, I get alpha prime prime of t is equal to, well, dv dt times t plus v times, well, dt dt. But we know the Frenet Serret equation for that, right? So this gives me dv dt times t plus the curvature. I get a velocity from the Frenet Serret equation times this velocity gives me velocity squared, and then the normal. So you might recognize this. This is the so-called tangential component to the acceleration, and this would be the, well, I would call it right now the normal component, right? But you may recall from physics, we use something like, we said AC is something like, v squared over r, where r is the radius of curvature. Usually we just talk about circles, so kappa is actually 1 over r, and so it's an inequality, right? But otherwise this is a local result. Alright, you and your BattleBot. Move it along there, mister. Where was I? For some reason I'm distracted. Alright, so anyway, this gives you, interestingly, the acceleration is not in the binormal direction, right? The acceleration is in the tangential. In the normal direction, those fill out the so-called osculating plane. Oh, just to draw a picture for a second here. So if my curve was something like this, and I could have my acceleration vector something like this, for example, and it would be, it has to be like that, though. It can't, acceleration vector can't point on the other side. It has to point towards the, if you think about the osculating circle, which I guess would be something like this, roughly speaking. Very roughly speaking. There has to be some part of the acceleration which points in the normal direction. So that would be the kappa v squared part, length of that vector, and then the tangent direction would be this guy. That would be dv dt. So in the case that the speed of the motion is not changing, constant speed, circular motion, for example, you just have a normal component to the acceleration, as we're hopefully well aware of from university physics. Now, so that's that. Just to show you an example, a kind of awful example, but an example nonetheless. So here we go. Hey, Daniel, cut it out, man. So here we go. We have alpha of t is, let's see, down just a bit. T squared. All right, kind of a weird curve. Here's its velocity. So there's its ugly speed, and that gives us this unit tangent field. All right. And then continuing that, yeah, this is very funny, Daniel. Continuing that, oops, do it like this. Continuing that, we have the derivative of t prime. Oh my goodness, that's quite awful. As you can see, product rule, and you got square roots, and after some simplification, I got to this, and so that would be just the derivative of t prime with respect to t would be that. So the magnitude of this divided by the speed is the curvature. And so there you go. There's the curvature function for this lovely curve. Now, I would point out that that's kind of the only way you can calculate the curvature here, unless you can actually calculate the arc length function directly. And I don't know about you, but integrating this directly, well, I probably could do it. It's just square root of 1 plus something squared. I suppose you probably could do this directly in terms of arc length if you wanted to, but it's nice that we don't have to. So, obviously, if you're actually going to do a bunch of calculations, it's nice to have some stone cold formulas. Obviously, t prime is alpha prime over the length of alpha prime. There's a little fine print there that needs to be addressed to because of the reparameterization issue. I think this, again, is in 72 to 73 on O'Neill. B, you can write as the cross product of alpha prime and alpha, the velocity and acceleration divided by the, normalized. The normal vector field you get by the cross product of the binormal and the tangent, which is different than what I've done so far. Now this formula is definitely wrong because the curvature is not a vector, so I think I'm missing a magnitude here. And I think that's supposed to be torsion. So the torsion depends on the, as you can see, third derivative, whereas curvature just depends on second derivative. Daniel, stop. Come on. Stop it. I gotta finish this, bud.
What time are you going to finish?
I'll be finished in about 5 minutes or so. So just go relax somewhere, please. Now, I think it's worthwhile to derive some of these slick formulas. So I'll try to, I'll try to derive this one at least. B is equal to, it's probably a useful exercise and a good learning experience to derive the other ones. I suspect it really tests your might in terms of your ability to manipulate vectors and derivatives and such. So I'll leave those for you to work out. But they're not in my notes, but they are. I do believe they are mostly, if not entirely, in O'Neill. So B is equal to this, right? Well, that's the question: is why is this true? All right, that's the claim. So, what to do, I would say, is to just look at alpha prime and alpha prime prime. So let's see, alpha prime prime. Daniel, stop. Alpha prime prime is equal to, as we saw up here, well, what is alpha prime prime? It's v prime t, right, plus vt prime prime, right? But on the other hand, we also know that alpha prime is equal to v times t, right? So that tells me that alpha prime is parallel to t, because in fact the speed is positive, so it's actually directly in the same direction, even not even better than collinear, parallel, angle between them 0. So as I calculate the cross product, right, if I calculate alpha prime cross alpha prime prime, well, that gives me, let's see here. Well, alpha prime actually I can just straight up write alpha prime is vt, right? And I've got that crossed with what? Well, with v prime t plus vt prime prime, right? Why do I have t prime prime? That's not right, just t prime. Duh. So t prime. And so what is this? Well, t cross t is 0, right? So this piece drops out, and we're left with v squared t t cross t prime, right? Now, I guess the question is, why is that in the binomial direction? Well, almost there. This is v cubed kappa t cross n, right? Because t prime is kappa vn in the non-unit speed case. But of course t cross n is just b. And so that gives us that this vector, alpha prime velocity cross acceleration, is in the same direction as b, since the curvature and the speed are both positive quantities. And consequently, normalizing, it stands to reason that b is equal to alpha prime cross alpha prime prime divided by the length of this vector. Right. Now the length of that vector in and of itself might be interesting, right? You can see that the length of alpha prime cross alpha prime prime is what? It's going to be equal to, well, this is a unit vector, right? So the length is v cubed times the curvature. And so I guess that gives you a formula for the curvature while you're at it. You can divide by v cubed, and that would give you a formula for the curvature. Oh, what do you know? I had that over here. Oh, I bet I forgot to zoom out.
Mm-hmm.
Daniel, you're making me look bad. I guess I can't really blame Daniel. I did it before. Alright, anyway, there it is. Sorry about that. Hehe. Just to run back through it again, alpha prime prime is v prime t plus vt prime. But on the other hand, alpha prime is vt. That means alpha prime and t are parallel. So if I take the cross product of the velocity and acceleration, I get the velocity cross the acceleration, but the piece of the acceleration which is tangential cross products to 0, which just leaves me with t cross t prime times v squared, but t prime is kappa vn, which gives me v cubed kappa times t cross n, which is b. Consequently, I get alpha prime cross alpha prime prime is in the same direction as b. Stands to reason that b is the unit vector. Take this vector, normalize it. There's one of the formulas in my theorem 2.4.11 in my notes. And also, of course, you can see that if you take the magnitude of both sides, it gives you this formula for curvature. Curvature is equal to the magnitude of this vector divided by the speed cubed. And there you go, there's a formula for the curvature, just in terms of the velocity and the acceleration and the cross product. The nice thing about these formulas compared to the thing I was just showing you in the example in my notes is we never have to differentiate. We don't actually end up doing this calculation. We just, because if you do this calculation and then you do calculate, you know, t cross n, in the process of doing that, this stuff is dropping out. But basically you're running lots of stuff you don't need to write. That's the insight of this formula. So in terms of specific curves, this could be very labor saving. And I was just trying to point out that the typo in my notes was that I'm missing a magnitude here, obviously. And that can't be curvature, it's got to be torsion. Oh, and look, that can't be a dot product. There's, well, I don't know, I guess that, is this also true? I don't know. I leave that to the reader. Finally, just to seal the deal here, there's a few additional theorems that are proved in O'Neill and typical books, and we've proved some of these. The rest of the things I haven't proved are very similarly proved. It's all based on the frame field technique, alright, and the Frenet Serret equations, but here they are. If the curvature is 0, the curve is part of a straight line. If the torsion is 0, the curve is planar, we prove that. If the curvature is constant and the torsion is 0, the curve is part of a circle, we prove that. If both the curvature and torsion are positive and constant, then the curve is part of a circular helix. Well, that's interesting. If the ratio of the torsion to the curvature is non-zero and constant, then the curve is part of a cylindrical helix. So, of course, the circular helix is a very, very particular case of that more general notion of a cylindrical helix. And with that, I will stop talking. That's about all I have for Lecture 6. We do have more to say about curvature torsion in the Frenet frame in Chapter 3, but we need to first understand the notion of an isometry, the notion of congruence of curves, so we can properly capitalize on the things we've learned here. Thank you.